Hey there, science fans! Welcome to another thrilling episode where we explore the wonders of science. Today, we're diving into the fascinating world of organic chemistry. This branch of chemistry is all about the study of carbon-containing compounds, which are the building blocks of life. Don't worry, it's not as complicated as it sounds. In fact, once you get the hang of it, you'll see how integral it is to our everyday lives. Organic chemistry is simply the study of carbon-containing compounds. These compounds are everywhere, from the simplest molecules to the most complex structures. And why carbon, you ask? Well, carbon is a very special element. It's unique in its ability to form stable bonds with many elements, including itself. Carbon's versatility allows it to create a vast array of structures. Think of it as the ultimate connector in the molecular world. Think of carbon as the Lego brick of the molecular world. Just like Lego bricks can be assembled into countless shapes and structures, carbon atoms can bond in various ways to form an incredible variety of molecules. It can form strong bonds with other carbon atoms, creating long chains and rings. These structures are the foundation of countless organic compounds. This unique ability allows carbon to form a mind-boggling variety of compounds, from the fuels we use in our cars to the complex molecules that make up our bodies. Imagine the diversity of life and materials all stemming from carbon's bonding capabilities. Organic chemistry is everywhere around us. It's not just confined to the lab, it's in our daily lives, influencing everything we do. It's in the food we eat, the clothes we wear, and the products we use every day. From the simplest sugars to the most complex proteins, organic chemistry is at work, and even in the air we breathe. The very oxygen that sustains us is part of the intricate dance of organic molecules. So buckle up and get ready for an exciting journey into the heart of organic chemistry. Together, we'll uncover the secrets of this essential science and see how it shapes our world in ways we never imagined.
Let's start with the basics. Hydrocarbons. These are the simplest organic compounds made up of only carbon and hydrogen atoms. Think of them as the backbone of organic chemistry. Hydrocarbons come in different flavors depending on the type of bonds between the carbon atoms. Alkanes are like a relaxed bunch with only single bonds between carbons. Methane, the gas we use for cooking, is a prime example of an alkane. Alkenes are a bit more lively, with at least one double bond between carbons. Ethene, a gas used to ripen fruits, belongs to this family. Finally, alkynes are the most energetic of the bunch, featuring at least one triple bond between carbons. Ethine, commonly known as acetylene and used in welding torches, is a classic example of an alkyne.
Now, let's add some spice to these hydrocarbon chains. Functional groups are like accessories that attach to carbon chains, giving them unique properties. Imagine a simple hydrocarbon chain like a plain necklace. Now, add a pendant, a functional group, and voila, you've changed its whole look and feel. For instance, the hydroxyl group, OH, is like a charming pendant that turns a hydrocarbon into an alcohol. Methanol, used as a solvent, is a simple alcohol. Another example is the carboxyl group, COOH, which acts like a sophisticated charm, transforming a hydrocarbon into a carboxylic acid. Acetic acid, the tangy ingredient in vinegar, is a carboxylic acid.
Here's a fun fact. You can have two organic compounds with the same molecular formula but different structures. These are called isomers, and they're like molecular twins with distinct personalities. Structural isomers have the same molecular formula but differ in how their atoms are connected. Think of it like building with Legos. You can use the same bricks to build a house or a car, same parts, different arrangements. Stereoisomers, on the other hand, have the same atom connectivity but differ in the spatial arrangement of their atoms. Imagine two identical necklaces, one twisted and the other straight. Same parts, different 3D arrangements.
Section 5. Naming organic compounds, the IUPAC system. With so many organic compounds out there, we need a systematic way to name them. Imagine trying to communicate about a specific molecule without a standardized system. It would be chaotic and confusing, right? That's where the International Union of Pure and Applied Chemistry, or IUPAC, comes in. Established in 1919, IUPAC has been the global authority on chemical nomenclature, terminology, and standards. IUPAC nomenclature is like a universal language for chemists, ensuring everyone understands what molecule we're talking about. This system eliminates ambiguity and allows chemists from different parts of the world to collaborate effectively. Think of it like giving someone directions. Just as clear directions help you reach your destination without getting lost, a clear naming system helps chemists identify and understand compounds without confusion. We need a clear and consistent system to avoid getting lost. This is especially important in fields like pharmaceuticals, where precise identification of compounds can be critical. The IUPAC system uses prefixes to indicate the number of carbon atoms in the longest chain, ensuring that the backbone of the molecule is clearly identified. Suffixes are then used to denote the type of hydrocarbon, such as alkanes, alkanes, or alkynes, providing additional information about the molecule's structure. And numbers are used to specify the location of substituents or functional groups, which are crucial for understanding the molecule's reactivity and properties. For example, the name 2-methylpropane tells us that the molecule has a 3-carbon chain, which is propane. The prefix methyl indicates a CH3 group, and the number 2 specifies that this methyl group is attached to the second carbon atom in the chain. Easy peasy, right? This systematic approach makes the complex world of organic chemistry much more navigable.
Section 6. Organic reactions, transforming molecules. In this section, we delve into the fascinating world of organic chemistry, where molecules undergo various transformations through different types of reactions. Organic reactions are all about breaking and forming bonds, leading to the transformation of molecules. These reactions are the backbone of organic chemistry, enabling the creation of countless compounds that are essential in our daily lives. Think of it like molecular Legos rearranging to create new and exciting structures. Just as a child can build endless designs with Lego blocks, chemists can create a vast array of molecules by rearranging atoms. Addition reactions involve adding atoms or groups of atoms to a molecule, usually across a double or triple bond. This process is crucial in synthesizing larger and more complex molecules from simpler ones. Imagine sticking two Lego structures together to create a larger one. This is similar to how addition reactions work, where new atoms are added to a molecule, expanding its structure. Substitution reactions, as the name suggests, involve replacing an atom or a group of atoms with another. This type of reaction is fundamental in modifying the properties of molecules, making them more useful for specific applications. It's like swapping out a Lego brick for a different one. By changing one part of the molecule, chemists can alter its function and behavior, much like how changing a Lego piece can change the overall design. Elimination reactions involve removing atoms or groups of atoms from a molecule, often forming a double bond. This reaction is essential in creating unsaturated compounds, which have unique chemical properties. Think of it like breaking off a piece of a Lego structure. By removing certain parts, chemists can create new structures with different characteristics, just as removing Lego pieces can change the shape of a model. Rearrangement reactions involve rearranging the atoms within a molecule to create a new isomer. Isomers are molecules with the same molecular formula, but different structures, leading to different properties. It's like shuffling the Lego bricks within a structure to create a different shape. This rearrangement can result in molecules with entirely new functions, much like how rearranging Lego bricks can create a new design. Section 7. Polymers, building blocks of giant molecules. Polymers are giant molecules made up of repeating structural units called monomers. Imagine connecting countless Lego bricks together to create a massive structure. These molecular giants play a crucial role in our lives. Natural polymers, like DNA and proteins, are essential for life itself. Synthetic polymers, like plastics and rubbers, are ubiquitous in our daily lives, from the clothes we wear to the packaging that protects our food. The process of forming polymers is called polymerization. It involves chemically linking monomers together, like attaching Lego bricks one after another.
Section 8. Stereochemistry, the handedness of molecules. Have you ever noticed that your left and right hands are mirror images of each other but not superimposable? Well, some molecules are like that too. This property is called chirality. Chiral molecules have a handedness, meaning they exist in two forms that are mirror images of each other, just like our hands. These mirror image forms are called enantiomers. Chirality is particularly important in pharmaceuticals. Just like one hand fits better in a glove, one enantiomer of a drug might have the desired therapeutic effect, while the other enantiomer might be inactive or even harmful. Section 9. Organic chemistry in our lives, from plastics to pharmaceuticals. Organic chemistry is not just an abstract concept confined to textbooks and labs. It's all around us, playing a vital role in our daily lives. From the plastics that package our food to the fuels that power our cars, organic chemistry makes our modern world possible. It's also at the heart of many industries, including pharmaceuticals, agriculture, and cosmetics. Organic chemists are constantly developing new materials and technologies that improve our lives. They're working on everything from more sustainable plastics to life-saving drugs. Section 10. Conclusion. Keep exploring the world of organic chemistry. Congratulations! You've just completed a crash course in organic chemistry. Well done! We've covered a lot of ground, from the basics of hydrocarbons to the complexities of stereochemistry and beyond. Remember, organic chemistry is the study of carbon-containing compounds, and it's everywhere around us in our world. From the food we eat to the clothes we wear, organic chemistry plays a vital role in our daily lives. Keep exploring, keep asking questions, and keep the spirit of scientific curiosity alive and thriving.